Okay, so we will start. Uh, I'm sure you watched the video I posted. What was the video all about?
Measure of variability
Measure of
on
the
the data set.
first check.
Okay, can someone enlighten me or at least ask what is measure of variability?
All about the spread of data in a given data set, sir.
Okay, it refers or talks about the spread of data in a given data set. Okay, that's correct. Now, what are the available measurements that we have when it comes to measuring variability? Hmm? What other measurements do you know? Anyone? Let's hear from Abalo. Abalo? Sumakag. You know what's the purpose if I posted the video and then you're not actually looking at it? It is a springboard for us to start quickly in our discussion. Yes, Iburan.
Unsa ganing question, sir?
What measurement of variability do you know?
Variance and standard deviation, sir.
Okay, we will start with variance and standard deviation. Of course, when you talk about measures of variability, this refers to the spread of data. We're trying to calculate um, how spread data or how spread the scores are in a given data set. So it's understood now that we're concerned of finding the situation of the data inside the situation of the data, how they are distributed in a given data set. So when it comes to measure of variability, now of course there is a way called measure of variability for group data and measure of variability for ungrouped data. Let's start with ungrouped data. The same with our measure of um, central location, there is also measurement for another formula for ungrouped data, and then there is also another formula for group data set. Let's start with measures of variability for group data. Take note, variability or dispersion refers to spread. Okay, this refers to the spread of data in a given data set. Now, very quick, aside from the variance and standard deviation, we have actually range. Range is somewhat also a measure of variability because range is simply highest score minus the lowest score. For example, the highest score is 90 and then the lowest score is 25. We have 65 as the range. Quick, we will simply identify now the range of the data. We're guaranteed that if this is the score, the lowest score, this is the highest score, guaranteed that the data is distributed within this interval only. Somehow, it gives us a picture of the distribution. The problem is it cannot characterize or it cannot totally describe to us the situation of the data set as to how they are close to one another in between. But we're guaranteed that that's the boundary, that the scores or the distribution of the data is just within this interval. Okay? That's why range is also measure of variability. In fact, it's the quickest measure of variability. Although its concern also doesn't give us a clear picture of how the scores or the data was distributed. Okay, that's one thing that concerns us the most. So I'll just quickly introduce to you what range is. Now let's move to our really focus this morning, which is about the measure of um, variability using standard deviation and variance. As far as I know, there were two formulas introduced in the video. Can someone recall what is the formula or what are the two formulas we have for measuring variability for ungrouped data? What is the first formula? Let's have Natinga. You know, it would be a lot easier for me to tell me that you don't know rather than you not responding. I really appreciate that you will honestly tell me that you don't have any idea. At least I know that I can proceed. Sunggayan. Yes, Sunggayan.
S for the variance, sir, S squared is equal to n times the quantity of the summation of x squared minus the summation of x squared divided by n, the quantity of n minus 1.
Okay. Carol, just give me, I'll just have to fix this. So, again, can you repeat that, Sunggayan? Sorry.
Okay, sir. For the formula of variance, S squared is equal to n times the quantity of the summation of x squared minus the summation of x squared divided by n, and the quantity of n minus 1.
Like this.
Yes, sir.
Now, this is, and what is the other formula? S squared equals,
Square root of variance.
no, that is the measure, that is for standard deviation, but I'm
I
referring
sorry,
to the
sir.
other formula. Hmm? We have
Sa sa group data na, sir.
ungrouped data. Actually, ungrouped data, I mean, ungrouped data, there are two formulas introduced. The other formula is the summation of x minus x bar, the mean square divided by n minus 1. Actually, these two formula are the same. In here, the process here is the mean was taken or at least solved first, and then that's the time we applied it solving the variance. Here, the formula of the mean is just embedded within the formula. That's why you notice there is minus n here, and then times n, because for all you know, uh, remember when you solve for the mean, that is the summation of all x's divided by n. Remember this formula? That's for the mean for ungrouped data. Now the same thing, that's why you notice there is an n here compared to this one, because here we have the mean already. In here, the mean was just embedded. The formula was just like, it was within the formula. In here, the mean was just actually computed first. So compute mean separately and then do the process. So either way of this one, they are both um, would give us the same answer. In this case, the only tedious thing about here is that when you compute the value, normally when you're mean, because mean is not necessarily whole number or integer, so the tendency here, your mean x bar would result to an integers that are, I mean, numbers that are non-integers. So it will be tedious because you have to play more with decimal numbers. But this one, the good thing about this formula also is that you are dealing with whole numbers and you just have to um, solve them. Okay? But like I said, whichever formula you're going to use, this is going to work. Again, this is variance for ungrouped data. Variance for sample. This is sample variance. Sample variance. Okay? That is for the sample variance. Now, of course, whenever we get the S or the standard deviation, that is simply the square root of our variance. The same also here. S equals the square root of variance. So in solving our formula, with whether we follow this one and this, our main concern is standard deviation. But before we get to standard deviation, we have to pass variance first. Later, I'll explain to you why there is such thing as squaring, and then why there is getting the square root. Now let's take some example and let's look at this example. Let's say we're concerned to find the daily rates of a sample of 8 employees at GSM Incorporated are the daily rates, okay? That refers to the uh, daily wage of employees of this company. 550, 420, 560, 500, 700, 670, 860, 480. So example, 8 employees. There were 8 employees. Let me just erase first this one. I needed a much bigger space. So you have 550, 550, 420, 560, 500, 700, 670, 860, and 480. 1, 2, 3, 4, 5, 6, 7, 8. Okay, these are the daily rate of the employees of GMS Incorporated. And then we are concerned to find the distribution, whether how spread is the distribution of this daily rate of this company. Now, let's try to solve this one using the first formula. Okay? Let's start with this one because I'm going to explain you why there is squaring of value later on. So first is we need to solve for the mean, of course. That's our prerequisite. In this situation, what is the mean of the data? So basically, we have to add everything. That's the summation of x divided by n. And now in this case, we have 500. You can follow me using your calculator. 500 for 20 plus 560 plus 500 plus 700 plus 670 plus 860 plus 480. So we have 4,740. 740 divided by Our divisor here is 8 because there are 8 employees, or of these 8 employees divided by 8. So roughly we have 592.50. So if this is in pesos, so this is the average daily rate of the 8 employees of GMS Incorporated. So we have now 592.50. Now, since we have this one, the next thing that we will do is we will get now the SS, or the so-called before we get the SS, the square difference, we will get first the difference of each daily rate minus the mean. So we have now, this is the problem, I don't have enough space. Okay, you have X, which is 550. Just bear with me with the numberings because I really need much bigger space, but I only have limited one. 420, 560, 500, 700, 670, 860, 480. 1, 2, 3, 4, 5, 6, 7, 8. Okay? And then the next thing that we will get is we will have X minus X bar. Okay, we will subtract the individual score with our mean. So this is what I'm telling you. That's why this one is quite tedious because of our decimal value. Okay, we have 592.50. So 592.50, that's 592.50 minus 550, that's 42. This is negative, negative 42.5. Next, 420 minus 592.5, that's negative 172.5. Then you have 560 minus 592.5, that's negative 32.5. Then 500 minus 900, 592.5. That's kindly please follow me and then double check if my values here are correct. Okay? So that we will not keep on repeating later on. This is positive 107.5. 670 minus 1 minus 122.5. 77.5. 860 minus 592.5. 26. 267.5. And lastly, 480 minus 592.5. Are all the entries I have written here are all correct? Have you double check it? Please.
Negative na, sir, ang last. Negative 100.
Ah, yeah, this is negative, sorry. Okay, let's try to add this one, this column. Let's add the second column, all of the summation of the second column, 42 point. Let's combine all the negative. 42.5 plus 172.5 plus 32.5 plus 92.5 minus 102.5. Okay. Plus 112.5 minus 107.5 minus 267.5. Ah, there's 777. Okay. Minus 77.5. What's the answer? What's your answer? If you combine all of this column with the negative and the positive, what's the result? Anyone? The answer is, did you get zero?
Yes, sir.
Okay.
Yes, sir.
Uh,
Zero.
how
Zero,
do
sir.
or how is it even possible that the result is zero? It's like this. Remember, mean here is your center. So we computed now the distance of all the score. Supposedly, I forgot to rearrange them. If you will arrange this one, there are certain scores that is below the mean, and then when you added all the scores below the mean, and then you added all the scores above the mean, and then combine them, the result is zero. Because basically, this is the center. So we're talking about now how, I mean, the average of the score, the distance of the score above the mean and below the mean, they are just equidistant from the center, which is the mean. Okay? So if we're going to add this all together right away, we can never find the distance or the average distance of all the scores away from the center or the focal. So the tendency is that's why we cannot really find the distance. No wonder we will need to square it. The squaring here, the sole purpose is to remove the negative value such that we can compute its variance or its average, its standard deviation. Because if we're going to add it right away, of course, a zero, we cannot find the standard deviation or the distance of the scores away from the mean when the result is here. That's why we need to square it. That's the purpose why there is a square root in our formula. Because we need to remove the negative, making it sure that the value are all positive. So this is now x minus x bar square. So we will square its value. That's 42.5 plus 172.5 plus, ay sorry, 42.5 square. This is what I'm telling you. When you are using mean, it will really matter. The decimal point will really make it tedious. And then followed by 29,756.25. Then you have 1,056.25 followed by 8,000. Please, I hope you are also doing the same thing on your end. Then you have 6,000, 6.25, 71,000. No, wait. I think I skipped one. 1, 2, 3, 4, 5. No, I skipped the 11,000. This is 11,556.25, 6,006.25, 71,556.25, and then you have 12,556, 600 rather, 600.25. Okay, and then you get the total, which the total is for 142,950, 142,950. Okay, you have now the value. Now, we needed all this information to solve for the mean using this formula. So we have now our value. So our variance, so you have s squared equals the summation of all the scores, I mean the difference of each score minus the mean squared divided by n minus 1. Our summation of this one is the summation of the third column, which is 142,950 divided by our n is 8. That's 8 minus 1. What is our variance. 142.950 divided by 7. So you have 20.42. 20.42. Again, we would then make our answer rounded to the nearest hundredths place. So we have 20.42, that is the variance. And then let's get the standard deviation, that is the square root of 20.42. Our answer is 20.42. 4.52 into decimal places, 2.52. Okay, this is our variance, and then this is our standard deviation. Okay? Do you have the same answer as you tried it also on your end? Actually, there is this such thing as somehow a general guide in interpreting the standard deviation. There is this book that I read, I forgot the author, said that when the standard deviation of the distribution is above 3, it means to say the data is quite spread. But if the standard deviation is less than 3, then the distribution is not that spread out. Okay? So in this case, since our standard deviation is 4.52, and if we follow that guide there, it means to say that the distribution is quietly spread out. Okay? So you notice the score also away from each other, considering that we only have 8 scores all in all. So that's how we solve the standard deviation and variance using the first formula. Any question or clarification?
And so far, sir.
Okay? So with this one, let's try to solve this problem using the first formula. And let's see if we will also arrive with 20.42. Take note of our answer. That's 20.42, the variance. And then 4.52 is our S. Okay, I'll just remove first this one here. So you have S squared is 20.42. Our S is 4.52. Okay, let's see if we will also arrive with the same answer. Okay, now let's use the erase all the given. Okay, using this formula, what we need is, of course, our actual score. I'll try to arrange down the score uh, from least to greatest. So we have 420, then I have 480, then we have
500, sir.
we have 560, 5, is it 560 na?
50.
50, sir.
60, 560, and then 670, 700, and then 860. 1, 2, 3, 4, 5, 6, 7. Okay, we have 8.
480, sir.
Yeah, we have 480. Next, we have here, the next column is we will get the square of each. So that's 420 square, 76,400. Then you have 480 square, that is
230,000.
230,400.
400.
100. Then you have
250.
250.
250.
500,
250.
250. Then what about 550 squared? That is 302,500.
200 to,
Correct? 560. Please do correct me if my data entered here are not correct. We have 670 square, 4, 4, 8, 900, 700. This is 490, right?
Yes, sir.
1,000. 860 square is
799.
700,600. Okay, we have this one, and then the next thing we'll do, we'll get the summation here, the summation also here. Okay, the summation of this one is 4,740.
4,740.
What about the other side?
2,951,400.
2,951,400.
951,400. Okay, now since we have this already, the next thing that we will do is substitute in our formula. So we have our n is 8. Our summation of x squared is 2,951,400 minus the summation of x, then square it, which is 4,740 square divided by 8 times 8 minus 1. Okay, let's find out the answer. That's 8 times 2,951,400 minus 4,740 squared and then divided by 7 times 8 is 50,
56, sir.
56. Yeah, 20.42, which is the same, right? And then our SD, the same, our standard deviation is just simply 20.42 squared, that is 4.52. Still, we will arrive with the same answer. But which do you think of the two formula is much easier to use?
Kana,
The
sir.
second one, sir.
Okay, this one because we barely avoid the decimal values because that is created because of the mean. But anyway, whichever is comfortable for you, comfortable to you do using, then let you can use it. Okay, you are not required to follow any of the specific formula unless stated. Okay, now we're good with this one. Measures of variability for ungrouped data, variance, and standard deviation. Now, the next that I would like to introduce to you is skewness. Who has an idea what is skewness? It was not in the video, but still this is also important because skewness will also determine, or not necessarily just determine, but also would describe the distribution of the data in terms of skewness. And then also this would also identify or help us understand the behavior of the data set, whether it's normal or non-normal. What is skewness?
We don't have any idea, sir.
Okay, let me read this statement first. Skewness can be detected informally by inspecting a graph on the distribution in your sample in in a form of, for example, a frequency polygon or a stem and leaf plot. Okay, so skewness can be identified using or through graph. However, quantifying them, meaning to say finding the skewness of the data by means of giving an answer of a number can be useful in deciding when the skewness is so extreme that you ought to take steps to modify your distribution in your sample or use different type of statistics. For this reason, most statistical packages provide a measure of skewness when the full set of descriptive statistics is requested. Where the variable is based on the average square deviation from the mean, skewness is based on the average cube deviation from the mean. Now, like this, when we talk about the standard deviation, this describes the distribution of the data set. Now, when you say skewness, this refers on the the skewness of the data, whether the data is skewed to the left or skewed to the right. When we have a data that is skewed to the left, meaning to say there is a longer tail of your graph, if it's in the graph form, there is a longer tail on the left side rather than the right side. If I'm gonna put it this way, okay, let's just use another example because we're using two large numbers here. If I may put it this way, example, if this is a graph, this is the graph of a normal distribution, meaning to say the left side and the right side, if this is where your mean is, the center, the left side and the right side are alike or identical, symmetrical for that sake. So in this case or scenario, we know that the left side and the right side are alike. But it is also possible that through the use of skewness, you will learn that there is like a graph like this. There is a longer tail here on the left side. Example, this is center. There's a longer tail on the left side. And it's also possible that you have a graph like this. There's a longer tail on the right side. So this is identified in terms of skewness. We can tell the skewness of the observation or the distribution by means of graphing. But in terms of quantifying them, finding the actual uh, skewness value of the distribution, then there is also a set formula. Okay? The skewness of the distribution used for ungrouped data. This is for ungrouped data. Okay? Take note of that. This is for ungrouped data. The formula for skewness is simply, let's just use the term SK equals skewness equals the summation of x minus mean cube over n minus 1 and then s cube. Okay? This is the formula. Now, for standard deviation, which is a measure of variability also, we found the standard deviation by means of getting the squared different deviation or the squared deviation. This time, we will get the skewness of the data in terms of cube based on the average cube deviation. So we will get the cube deviation of all the scores. So earlier, standard deviation was found using the cube deviation, a square deviation of each score. This time, we will find the skewness in terms of cube deviation of the score. Okay, this is our formula. This is again skewness for sample size, sample. Okay, and then for population, that's another formula also. Now let's take some example. Let's say our data we have a score of Mhm. Let's say we have four score. Actually, example, this is our sample. We have 2, 5, 2, 3, 5, and 10. We have 4 scores. And but before I'll proceed with skewness, so why don't you find what is the standard deviation, the variance, the standard deviation of this distribution? Well, also with also here on my end. That's 2, 3, 5, 10. I would like you to use the first formula. Who can give me the first answer, the first correct answer, please? Use the first formula wherein you need to use the mean. What's the answer?
5.
The mean is 5. Yeah, that's correct. What is the variance? That was n minus 1, right? The summation of x minus x bar squared divided by n minus 1. Is that our formula? Right? Hello? Oh, what's the standard deviation?
12.67, sir.
What is happening to me? Okay, our SD is 12.67
12.6.
and our variance is
3.56, sir.
the variance.
12.67, sir.
No, standard deviation is 12.67, but I'm asking for the variance.
3.56.
Ay, wait, what is so long? Our variance is 12.67, while our standard deviation is
3.56.
3.56.
3.56, okay? Please forgive me. I am already confused with my solution. So we have already our value. Our standard deviation is 3.56. Okay. Now the next thing that we will do is we are gonna find the skewness of this distribution, whether this is skewed to the left or positively skewed or skewed to the right. Okay. The next that we will do is let's form our table. X that is 2, 3, 5, 10. Then you have, of course, we will have X minus X bar. Our X bar here is 5, correct? The mean is 5. So you have negative 3, negative 2, 0, and then 5. And then, of course, our X minus X bar cube. Okay, our concern now is the cube. So we have now the value of 27. That's negative, right? And then this is negative 8, 0, and then 125. Okay, let's get the summation of that column. Our our S here is, what was our S? S is 12.67. Our S squared, our S is 3.56. That is 125 minus 27 minus 8. That's 90. Okay, so let us now solve the skewness. So you have the numerator is 90 divided by our n is, okay, that's 3 times our SD, that is 3.56 cube, which is 90 divided by 3 times 3.56 raised to the power of 3, close. We have positive or negative? What's your answer? Three times 3.56 cube. 90 divided by 4 times 2.56 close. What's your answer? 90 divided by, hello?
Yes, sir.
What's your answer?
0.66, sir.
0.66, sir.
Okay, 0.66. This is our skewness. Now, how do we interpret this one, the skewness? It's like this. When the result here is 0.66 or positive for that example, that means to say we have here, this is an example of positive skewness. Positive Okay, we have the positive skewness, or the data has a positive skewness. That means to say the data is somehow like this. There is a longer tail towards the right, towards the positive value. It's clear because if you look at this one, 2, 3 are very close to 5, which is the mean, while there is an extreme value of 10 towards the last. Okay? So this is an example of a non-normal distribution. Okay? How do I know that it's a normal? Because our skewness is zero point zero 0.06. If the distribution is having a negative skewness, that means to say it would fall like it will resemble a graph of like this. There is a longer tail here in below, meaning to say there are um, extreme values of your distribution on the negative side or less than the mean. Okay? That is positive skewness and negative skewness. Now, if your data is like this, or the graph of your data is like this, meaning it's normally distributed, it means to say your skewness is zero. This is zero skewness. Okay? The skewness of the distribution is zero when it is normal, normal distribution. Okay, are you with me?
Yes, sir.
Because if you're going to subtract that
Yes,
one,
sir.
and the tendency is um, the left side and the right side are just equal. They have an equal tail. When it comes to the curve or the tail of our graph, they are just asymptotic. Not asymptotic, but they are symmetrical. So symmetrical identical. So that means to say, once subtracted, the answer is zero. Because the negative is equal to the positive side of the distribution. So once combined, the result is zero. So the distribution is zero. But if it is like this is an example of a negative skewness. While this one is a positive or has a positive skewness. So somehow, identifying the skewness of the distribution would tell you whether, or at least give you a picture of your distribution, whether the data is skewed to the left or skewed to the right. As it is distributed around the mean, we are going to find out now where is the dominant tail of your graph? Is it to the right or to the left? If it's to the right, that means to say you have a skewness of positive. And then if it is skewed to the left, then there is a skewness of a negative number. So if this is negative, then somehow would resemble to a graph with a longer tail here on the left side. If it is zero, then that means to say you have a normal distribution. So basically, looking at the skewness of the data, you can make some changes because in analyzing a data in statistics, normally everything is treated once it's normal. If not, then there's something that you have to do about your data. It's either you are going to treat the data, meaning to say it's like you're going to do something about the data because this will going to signal you that something is not right, something is off, something like that. So how am I going to put this as in an actual exact situation? Example, if in a quiz, if there is an extreme low score, that would, if you are going to graph the distribution of your students' score, if there is a extreme low score, you have a negative skewness. So you will know that there is really someone that is really struggling, that you need to do some remediation, some sort of that idea. If there is also a positive skewness, extreme, higher score, it might also indicate that someone perhaps is cheating, more or less, something like that. There are some implications that will take place when you will, because these are actually would signify whether there are extreme values or results. So when the distribution, when your skewness is zero, then that means to say the data is normally distributed. You have to understand that when you have a normal distribution, your mean, median, and mode are the same. Okay? And then it's a unimodal data. You have a bell curve, like the graph is bell shaped, and then uh, symmetric. Those who are with me in Math 101, I suppose you understand the meaning of symmetrical. So this side there and this side here are just exactly the same from the point of perspective, which is the center, which is now our central tendency. Am I making sense? Hello?
Yes, sir.
Now, we're done with the skewness of the data. Another thing that would help us identify or at least know the measure of variability is the so-called cortosis. Cortosis. What is cortosis? Who has an idea of what cortosis is? Anyone? Let's hear from Kumahig. What is cortosis?
It is a statistical measure used to describe the degree to which scores cluster in the tails or the peak of a frequency distribution.
Okay, it's like this. The skewness of data, we're now trying to test the tail. Okay, try to look at this one. If skewness is we're concerned with the tail, whether longer to the left or to the left or to the right, that's skewness. But when you say kurtosis, we're concerned of the peak. Okay, the peak of the data. You have to, if I'm going to illustrate it, example, if I'm talking about normal distribution, so normal distribution like this, how I'm gonna draw it, like for example, okay, and then let me have another one. Try with my drawing. Now, basically, if you look at this one, this is supposed to have a shorter. Whenever you have it this way, you have a shorter tail, but higher peak of the graph. And then this one is the normal, and then this one is longer tail with lower peak. The peak of the graph is shorter than this one. By the way, but to sum it up, you notice that they are both normally distributed. Okay? When it comes to their skewness, the skewness of all of these are zero. It's because these are both normally distributed data. But they are not the same. One is too high, another is just average, the last one is too low. So the peak, the kurtosis of the three graphs are not the same. Although they're both, what do you call this? So they're both normally distributed data. Bell shape, check. Unimodal data check. Skewness zero, check. But the problem is they are not the same. Because it's not guaranteed that the skewness is zero. When you have, example, you have two distribution. Okay, two. So this is the first distribution, second distribution, and let's say that there are three. Third. It doesn't mean that the three, both the three distribution, they are normal. Because they have the same unimodal data. They have the same data unimodal. And then the three graphs are having skewness of zero. So if you base the three on this one, it seems that the distributions are the same. But if you look at their kurtosis, they have different peak. So a higher peak would lead to a shorter tails. Okay, the tail here is shorter, while this peak here, which is the peak is average, is just have also a just longer than this one, the longer tail than this. While this one has a longer tail than all of this, but shorter peak. So it implies now that they're not exactly the same. So looking at the three conditions would not guarantee that they are alike because the peak of the graph or the peak of the distribution would also tell you. Okay? So all the more that what I'm telling is the three observations or the three distributions are not identical. They differ in terms of their peakness. Now, what they call a kurtosis or a distribution with this kind of kurtosis, this is called leptocortic. Where are you, leptocortic? Let's see the spelling. Okay, this is called leptocortic curve. Leptocortic curve. Okay? Meaning to say that the peakness of this one, I mean, there is a higher peak. Okay, there is a greater peak. While this one, the average one is called the mesocortic. Mesocortic. Why we're talking about curve here? Because we're measuring the curve, this one, the curve here. Okay? That's why we're talking about mesocortic curve, leptocortic curve. If you have a curve of like this in your distribution, this is called the laticortic cortic curve. Okay, so which is also some would help you identify the distribution of the data set, the spread of the data. Because if the data is widely spread, the tendency is you will have, if it's widely spread but normally distributed, you would end up with having a platycortic curve. If the distribution is normal but not widely spread, then you will have a mesocortic curve. But if you have a distribution that is normal but very tight, very close to one another, then you have a leptocortic curve. Am I making sense? Hello?
Yes, sir.
Now, how do we compute the kurtosis? Okay, how do we compute the kurtosis? For the computation of the kurtosis for sample, I'm still on sample, okay? So everything, they are all on sample. The first example I gave you was measure of variance and standard deviation per sample, then skewness per sample, and then kurtosis per sample. Okay? And these are all under ungrouped data. Let us have now the formula for kurtosis. The formula for kurtosis, if the standard deviation is using squared deviation, that's for the standard deviation. The skewness is the cube deviation of each scores away from the mean. The kurtosis is the fourth, okay, the raising the it's like fourth deviation, okay, raised to the power of 4. If this is cube, the next is fourth. So we have now kurtosis. I don't know what's the let's say we have the kurtosis. Kurtosis is equal to the summation of x minus x bar to the power of 4 divided by n minus 1 times standard deviation based to the power of 4. That is the kurtosis. I will not follow this book because I noticed that this book introduces minus 3, but in some other article I read online, there's no minus 3. I'll just follow this one. Okay, we have, this is the formula for the kurtosis. Now, for the kurtosis, let me just read to you what will happen for the kurtosis or how do we interpret the kurtosis. Okay, it says here, kurtosis is a measure of whether the distribution is too peak, a very narrow distribution with most of the responses in the center. That is kurtosis. While skewness is the extent to which a variable distribution is symmetrical if the distribution of responses for variable stretches towards the right or left tail of the distribution, that is spread to the left and spread to the right. Okay, when both skewness and cortosis are zero, if your cortosis here is zero as well as the skewness, that means to say uh, that researchers are very unlikely to ever encounter the pattern of responses is considered normal distribution. Okay? So, and the distribution is normal. A general guideline for skewness is that if the number is greater than 1 or lower than 1, that is positive 1, greater than positive 1, greater than or equal to positive 1, less than or equal to negative 1, this is an indication of a substantially skewed distribution. So it's either skewed to the left or skewed to the right. But for kurtosis, the general guideline is that if the number is greater than positive 1, the distribution is too peak. Likewise, if the kurtosis of the distribution is negative 1, it indicates the distribution that is too flat distribution. Exhibiting skewness and kurtosis that exceeds the guidelines are considered non-normal. Okay? I hope we're getting that part there. So if your kurtosis is greater than or equal to positive 1, we have too peak or the peak is too high. And then if we have a kurtosis that is less than or equal to negative 1, then it's expected that we have a very flat also the distribution, yielding to a platycortic. The other one, the too high, is leptocortic. If the kurtosis is zero, the same with skewness, then we understand that the data is normally distributed. Okay? Am I making sense? Hello?
Yes,
Yes,
sir.
sir.
Okay. Now let's compute the kurtosis of this distribution where you have 2, 3, 5, and 10 as our distribution. So all that we need to do is we'll just get the x minus x bar to the power of 4, right? That is to at least find out the kurtosis. So that is, what's the value? Okay, this is 81. This is 16. 125 times 10 times 5 is 625. 625 and 0. Get the total plus 16 plus 81. This is what I'm telling earlier. Because if this is the case, whenever we'll encounter a value that is negative, if this is the case, anyway, let's just find out what will be the result for this one. If it has a zero or whether it's leptocortic or platycortic. Because I'm suspecting that we will never get a platycortic. I mean, we'll be missing the platycortic situation because according to the book, the one that I followed, that is from Barron, in order for you to get the negative value is that we subtract with 3. But most of the formula I found online, there is no minus 3. So let's try to find out. Mhm. The kurtosis are all positive. This is what I'm suspecting because this is the explanation of the other author. Let me just read to you what the author said here. The calculated value of negative 1.5 suggests that the population from which the 4 numbers were drawn has negative kurtosis, somewhat lighter tails than the normal distribution in practice. However, one should never wait. I am looking where is the explanation why there is minus 3. I hear. Notice the change of the third to the fourth power and blah blah blah. Subtracting 3 ensures that the kurtosis of the normal distribution will come out 0. Thus, a distribution that has relatively fatter tails than the normal distribution and greater peak will have a positive kurtosis. It will be leptocortic, whereas a relatively thin tail, less peak distribution will have a negative kurtosis. It will be platycortic. In fact, unless you subtract 3, the population kurtosis will never be less than positive 1 after you subtract 3. After you subtract 3, the kurtosis can range from negative 2 to positive infinity. This is actually what I'm confused about, which somehow I subscribe with this book. It's because mostly if you look at this one, from this formula alone, this will never gonna give us a value of less than would give us a negative value because there is no negative expand. You can never get a negative value for this one because this is raised to positive. I don't know if I hope I'm making sense to all of you. Do you understand me? Have you realized what I have just realized? Hello? What I'm saying is that, do you notice the value here? The exponent here is even. So whenever the exponent is even, technically everything here will be positive. Now, since it's positive, there's no way that the kurtosis will yield a negative answer. Which earlier I told you that when the kurtosis is negative, then it means to say it would yield to a negative uh, a negative kurtosis would somehow become a platycortic curve. Thin, a longer tail, and then flat peak. But that's what I mean. That's why this book is said that there must be a minus 3. Actually, the formula here, there is minus 3. But I'm confused because the other source said that there is no minus 3. I'm really confused already what's really the formula. Let's wait. Let me try to check if we can find a better resolution for this one. Population for Kurtosis. Let's try to check this one. Because in this situation, all the kurtosis are positive, which the explanation of kurtosis cannot be, or we will say that when the kurtosis is negative, then it's platycortic. But it doesn't. I'm confused. Maybe you have there some guide also. No, all the example here, they are all positive. There's no problem with the skewness because definitely this is gonna yield a negative answer sometimes because of the our exponent is odd. So whenever his exponent is odd, we will not eliminate the negative numbers like this one. But for whenever your exponent is positive 4, then all the answers will be positive. Anyway, how are we gonna reconcile this one? Okay. Can you please do some searches also? Where can we can meet this one? Because how do we interpret skewness and kurtosis value? This one says that positive 1, negative 1. Then positive 1, negative 1 also for kurtosis. The problem is, let's look at the formula. How do you calculate the skewness? For kurtosis, there is no negative 1, a negative 3 for kurtosis. But my question, if there is no negative, how do we get a negative kurtosis when this is all positive? Well, let's just leave it this way. Probably it's possible because of the denominator. Anyway, let's just have it this way, settle from this here. That was just my, those were just my theory. Anyway, so let us solve for the kurtosis of this one. We have there 625, that is 625 divided by 4 times, what is our S? 3.56. 3.56 raised to 4. Oh, what's the answer? What's the answer? 4 times 625 divided by 625 as divided by 4 times, I'm sorry, 4 times 3.56 to the power of 4. We've got 0.97. Do you have the same answer? 0.97.
Yes, sir.
Do you have the same answer?
Yes, sir.
Okay, somehow we have here an answer that is leptocortic, or this distribution is leptocortic because our the thickness are both positive. The skewness is positively skewed, and then but you notice it's closer. You notice the value is closer than 0. So this is somehow very close to a normal distribution because remember, when the skewness and the kurtosis is 0, it's a normal distribution. It's a normal distributed data. So more or less, since this is quite almost to 0, then there is a chance that it's closer to normally distributed data. But we
Yes,
cannot
mister.
disregard. Yes.
Kanang regarding sa kanang kind sa cortosis curve, sir ba? Na by range if pila kutob ang na under sa cryptocortic, like for example, 0.97 ay 0.66 to
Actually, that's also
0.97.
what I would like to find out. But based from the reading that I have, based from this explanation, that means, I think I closed it already.
So wala siya exact nga range, sir.
Uh, the range given here earlier, the one that I read was positive 1, greater than positive 1, and less than positive 1. If it's the cortosis is positive 1, then that is somehow also like a leptocortic, and then negative 1 is platycortic. So if this is 0.97, so it's somehow it's outside the positive and the negative one. It's within between that one that is closer to the mesocortic. If that's how I view it, because based on the explanation from whose author is that? Hey, where is that? I think this one. No. Based from the for I can no longer find that author. But what it says there is that when it comes to the kurtosis of the distribution, positive 1 and then negative 1. When the distribution is positive 1 above, that means to say that the data is um, having a relatively, the word there is relatively. So relatively uh, too peak, and then when you have also negative one, that's relatively too flat, giving us the idea of a leptocortic and then the idea of platycortic. Okay, I hope I answered that one. I forgot where I cannot find anymore the link where I read that. Let's look at this one for a while. Any other clarification? Okay, wait. This is just a histogram. This one just give us a summary that a kurtosis tells you how tall and sharp the central peak is relatively to the standard bell curve. So by the way, the observation for this one is just the normal. Okay, the standard bell shape. If the standard bell shape kurtosis is zero, that's why the range given earlier, the one I told you is that positive one and then negative one. Because the between if we're going to range it between one positive one going to negative one, that's where the positive and the normal distribution is very much close with. But if you go beyond the positive one above and then negative one below, that's the time when your cortosis value is positive one above. That's where the leptocortic would, meaning kasi there is a relative peak already, or the peakness is quite relative. And then if the value is negative 1 below, that will give you a platycortic curve. That's all that I have for now.
Sir, ang kanang sa calculation nimo sa Cortosis, sir ba?
Hmm.
4 lagi gihapon, di ba? N minus 1.
Ay, sorry, this is 2. This is 3.
1.30 ang answer, sir.
What's the answer?
Yes, sir. 1.30.
1.30.
1.30.
1.30?
Yes, sir.
1.30, sir.
Yes, sir.
Okay, thank you for clarifying that one. So in this case, we have uh, a platycortic, not the mesocortic, because it's already outside. It's already greater than 1, positive 1. Because earlier, when we only have zero point 0.9, zero point 0.9, that is somehow which is still within the mesocortic curve range. But since we go outside already the mesocortic, and then it's positive, then we are moving to the leptocortic situation. If we go down to negative 1, example, negative 1.2, going to the negative values, then that's a platycortic. Okay? Thank you for that correction. Any other corrections or clarifications? Hello?
Sir, can you
Hello?
give another example, sir, nga ma-under siya sa mesocortic?
Mesocortic. Actually, I'm looking for an example here. Most of the example does not describe, they don't focus on the mesocortic and the leptocortic or platycortic curve. Because I cannot just produce an example right now that would give us this one. But let us try to look for a normal distribution. I don't know if there is an example of a normal distributed data. Let me try to see if we can find an example. Yeah, for sample Cortosis, really there is no -3. I don't know the author, the author, the book that I'm using why there is -3. Well, he has here excess Cortosis formula. Very often, the Cortosis is quoted in the form of excess Cortosis relative to normal distribution. Excess cortosis is simply cortosis less 3. The excess cortosis formula thereof is this is the explanation why there is minus 3. This computation with the minus 3, that is finding the cortosis relative to the normal distribution. Because according to this explanation, very often cortosis is quoted in the form of excess cortosis, meaning to say cortosis relative to the normal distribution. So it like was referred to the normal distribution. That's why it's minus 3. Because if it's referred to the normal distribution, that's the tendency that we can get a cortosis of a negative value. It's called excess cortosis, which is in the book that I followed. There's no excess cortosis term that appeared there, but this article explains why there is a minus 3. It says that the formula is minus 3. The cortosis and excess cortosis formulas above are the population cortosis when your data set includes the whole population. Very often you don't have data for the whole population and you need to estimate population cortosis for sample. For a very large sample, very high, the differences between among n plus 1, n, and n minus 1, n minus 2, n minus 3 are becoming negligible. And the sample cortosis approximately equals to... okay, sample excess cortosis differs from sample cortosis formula only by adding a little at the end. Yeah, there is just minus 3. For a very large sample, because this one has another consideration. They consider the population, sample, and then there's also large sample. Not necessarily population, but the sample is very large. Which I don't have again the range when to say that it's large and when to say it's not large samples. But technically, when you encounter a computation for cortosis with a negative 3, minus 3 here, that is called a cortosis, excess cortosis, which the computation of cortosis is referred, or which is quoted from the the normal distribution when you encounter a minus 3 in the formula. And then the one that was asked earlier, whether there is an example of a normal distribution. Let's see.
Excuse me, sir.
Yes.
Sir, sa imong Cortosis, sir ba? Manong 625 total? Dili na siya
Ah,
7,
my gulay. Yeah,
sir.
yeah. Yeah, I get it.
Kanang,
I forgot to add the rest 85, 81, and 16.
yes, sir.
That's
722 siya tanan,
81.
sir. Then 1.50 ang answer.
What, 722? Why I
Yes,
copied
sir.
it? Yeah, I solved this
722.
earlier already, and then the answer is not 625. 722, and then what is the cortosis?
1.50, sir. 1.50.
1.6. So,
50.
1.50.
huh?
50, sir. 50.
1.50, sir. 1.50.
50.
So still it is leptocortic,
Yes, sir.
or at least it falls on the leptocortic curve because it's already greater than positive 1. So much for that. What was I was trying to explain earlier? Anyway, I'm looking for the example. I cannot really think of an example right now that will give you as a value here, but they definitely, when the cortosis is 0 point something, that's less than positive 1 and greater than negative 1, then it is somehow would fall on this type of curve, mesocortic curve. It's because in that situation, our cortosis is outside the positive 1. I mean, the range between +1 and -1, where the mesocortic curve is somehow is situated, because mesocortic is somewhere where the cortosis is 0. So, but when you go out, it's like if this is 0, this is 1, this is -1. If you are just laying between this area, going this area between positive -1, somehow that's where the mesocortic curve is playing. But when you go here, that's +1 above, that is already leptocortic. And when you go down here and then go down here, that's the platycortic. Okay? Because I cannot really think of a normal distribution. I mean, a given that has a normal distribution. You cannot just invent a given that will guarantee a normal distribution. Any question? Oh, please. Do you have question? Any question, please?
None so far, sir.
Okay. For this time, since no more question, we will just end here first, and then I'll try to check whether if we still need to discuss about the group distribution. Okay, I'll try to check about that. Maybe we will discuss group distribution. I'll just try to check because I have to verify some of the formula. Like this one, the Kurtosis, when do have a -3, because the book that I'm following, there is a -3, but it does not explain excess Kurtosis, which was actually happening whenever the Kurtosis was calculated, quoted from the mean, quoted from the normal distribution. So this type of Kurtosis where there is no minus mean, I mean -3, it does not really quoted from, I assume it's not quoted from the normal distribution, but it's just plainly computing the Kurtosis, the peak of the distribution. Okay? So much about this one. You can open your camera. I think we'll just end here. Are you tired? Okay, so I'm not gonna give you the quiz after this one because I think the lesson was just so exhausting. So what we're going to have on Thursday, I'll give you a quiz. So sooner when we will have, I mean, by Thursday after our quiz, I'll just see if I'll be able to prepare a quiz that is just a quiz within an hour. Then there will be a class discussion afterwards. But if I can prepare a quiz that is more than an hour, then I may not meet you already. We will just have our next meeting next Tuesday. Okay? Because I still have to at least review some of the items that I can include in your quiz.
Sir.
Okay? Anyway, this is just easy. As long as you have the formula, you follow the steps, things were just very easy. Okay? So with that saying, you can now say bye to your classmates and you can go.
Hi, classmate.
Bye,
Classmate.
classmate.
Bye,
Bye,
classmate.
sir.
Thank you, sir.
Bye.
Bye.
Thank you.
Thank you, sir.
Bye, sir.
Bye.
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 Bye,
Thank
sir.
you, sir. God bless. Bye, sir.
Bye. Ram, magkuha na og kanyang sudan. Nag-resign nito ng whiteboard rambe.